Thank you, Gary, for the introduction. Today, I'm very happy to be here to tell you about how to think about gravity and how to think about space-time geometry and how all of that appears out of something amazingly different, that the idea of quantum error correction comes into this, the idea that we can somehow protect quantum information from decoherence in a computer. And I'll tell you all of that today. But before we get to all of that, I'd like to start by noting something more familiar to many of you. So I'd like to start by saying something about the amazing success of the standard model of high-energy physics. So this model is a fundamental description of three of the four fundamental interactions in nature: the electromagnetic, the weak, and the strong. What's missing, however, is a fundamental description of gravity, the fourth and the oldest known interaction. We would expect that such a description should somehow incorporate the rules and principles of quantum mechanics, just like the standard model does. But this is a very difficult question, and we don't know how to do it. In particular, understanding this difficult question would reveal to us the quantum nature of space and time. So let me start by putting this problem into perspective. Understanding quantum gravity has been a long-standing goal of theoretical physics for about at least 60 years, going back to many physicists, including Feynman, DeWitt, Wheeler, and 't Hooft. Initially, people tried to somehow quantize a metric as a local field, but that quickly ran into many difficulties. By now, we know that this is not the correct way of thinking about quantum gravity. Starting with Shirk and Schwartz, it was gradually realized that string theory provides a much more satisfactory perturbative definition of quantum gravity. It's a perturbative theory in the sense that analogous to how we do Feynman diagrams in quantum field theory. So it's not a complete description of the theory. The perturbative expansion only provides a useful description at weak coupling and is useless at strong coupling. We'd like to understand what is the non-perturbative description of quantum gravity. And in the last 20 years or so, we have seen the discovery of such non-perturbative descriptions. We have, in fact, seen two of them, the BFSS Matrix Model and the so-called ADS-CFT correspondence, anti-de Sitter Conformal Field Theory correspondence. I'll say more about these as we go along, but I'd like to start by mentioning that these two theories both have the surprising feature that they are holographic. What that means is that the microscopic description of the theory lives in fewer dimensions than the effective gravitational description of the theory. It's not quite surprising that the same theory may have a microscopic description and an effective description. For example, hydrodynamics is an effective description of water, which consists of atoms, which consist of protons and neutrons and electrons. What's amazing here is that the two descriptions do not live in the same space-time dimension. And that's why they're very special, and we call that holographic. In particular, the BFSS model uses matrix quantum mechanics, so that has only one spatial dimension and only one time dimension and no spatial dimension, to describe gravity in 11-dimensional flat spacetime. The so-called ADS-CFT correspondence uses conformal field theory in d dimensions to describe gravity in d+1 dimensions. I'll say more about this duality as we go along, but the picture is roughly this. We have a boundary theory in d dimensions describing gravity in d+1 dimensions. This immediately leads to two natural questions. The first is, why should quantum gravity be holographic? Why should it behave in this way? And the second question is, how can this be the case? How can a lower dimensional theory describe gravitational physics or approximately local gravitational physics in higher dimensions. In this talk, I'll review the answer to the first question, and I'll describe a new and I think much more concrete answer to the second question, but I'll do it in the context of the ADS-CFT correspondence. Let me first introduce what's the difficulty. The real difference between gravity and the other interactions of nature is that gravity is universal. This implies the existence of black holes. And when two black holes get too close to each other, they collide and form and emit gravitational waves, such as those that we saw in 2015. Classically, we understand black holes very, very well. We can simulate them and generate all kinds of nice plots. But quantum mechanically, they are the main obstacle to forming a microscopic description of quantum gravity. The problem is that because gravity is universal, it's not possible. We cannot use the kind of local variables that we use to define normal quantum field theories, such as electrodynamics. If we try to do that, if we try to define local observables in a theory with gravity, for example, we might try to look at define an array of rods and clocks to measure lengths and distances. And if we try to do that and try to do it in a way that the lattice spacing is Planck-sized to be able to define distance to very good accuracy, then this array must be very, very heavy to be localized because of the uncertainty principle. This immediately creates a black hole, and we lose control of the description. I think the tension is most dramatically illustrated in the so-called Bekenstein-Hawking entropy for Bekenstein-Hawking formula for black hole entropy. So apart from a number of fundamental constants here in this formula, it's telling us that the entropy of the black hole is proportional to the area of the horizon. It's important that it's proportional to the horizon area, not to the volume of the inside. In particular, this means black hole entropy is not extensive. So in holography, we have a lower dimensional microscopic description that describes higher dimensional gravitational physics. The lower number of dimensions in the microscopic description is what enables us to get the right black hole entropy. This answers the first question I asked earlier, which is, why is quantum gravity always holographic? For the second question, the second question was, how could lower dimensional theory describe gravitational physics in higher dimensions? So for this question, I will need to introduce the context of ADS-CFT. So let me do that. So the anti-de Sitter conformal field theory correspondence was a conjectured duality or equivalence between two theories. The two theories are formulated in a way that the first one involves gravity and the second one does not. So on one side of duality, we have quantum gravity in this asymptotically anti-de Sitter space. Anti-de Sitter space is the simplest, maximally symmetric space-time with constant negative curvature. It can be conformally mapped to the interior of the cylinder, and time goes in this way. At the fixed time slice, we simply have a hyperbolic manifold. So quantum gravity in this space is actually equivalent to another theory, which is a normal quantum field theory that doesn't have any gravitational physics, and it lives on the asymptotic boundary of this space-time. So it's on the cylinder, and it has a special symmetry, the so-called conformal symmetry, which essentially says physics at the larger scale is indistinguishable from physics at a smaller scale. So such a conformal field theory turns out to be exactly dual to quantum gravity in ADS space. This is a concrete example where something amazing happens, that space-time and gravity emerge from a non-gravitational system, in this case, the conformal field theory on the boundary. There are many realizations of such a duality. The most famous one is probably string theory, a certain type of string theory known as type 2b, on 5-dimensional ADS space times a 5 sphere, and that's dual to the so-called supersymmetric Yang-Mills theory with SUN group, gauge group. The supersymmetric Yang-Mills theory is simply a non-abelian version of the quantum electrodynamics, and now we have supersymmetry added to the theory. I want to emphasize that our universe is very different from this space-time. Our universe is not anti-de Sitter space. It has positive curvature instead of negative curvature. So this is a toy model, really, for describing what could happen for our universe. This is a toy model of quantum gravity that we can use to perform laboratory experiments, thought experiments, and this will eventually be useful for understanding quantum gravity for our realistic universe. I also want to get to some of the details that we need to understand about this duality. So it's a quantum equivalence. That means we can map states from one side, for example, the bulk state, into a boundary state. We can map quantum numbers or conserved charges from one side to the other, including the Hamiltonian or the angular momentum. On one side of the duality, we have gravity. On the other side, we don't. So what's Newton's constant, G, mapped to in the other side? It turns out it's mapped to 1 over n squared, where n is the rank of the gauge group. So in the so-called large n limit, we will find weak gravity and an approximate description in terms of classical gravitational physics, general relativity, and their generalizations. And one more thing that I need is how to describe operators from one side to the other. In particular, in the conformal field theory, very useful objects to study are local operators that has a particular weight, a particular dimension. Let me describe those as O of x. The way to get that from the dual side is to take a corresponding bulk operator, phi, that lives in anti-de Sitter space, and then pull it to the boundary. So R goes to infinity is really going to the boundary of that space-time with some compensating factor determined by the conformal dimension of the operator. So this is how the correspondence works in terms of getting local operators in the CFT. Using these rules, now it's easy to understand scattering experiments. If we do a scattering experiment in ADS, what we are really studying are correlation functions in the CFT. For example, we can do 2-to-2 scattering, and this corresponds to a 4-point function in the CFT, which we can easily compute, at least in principle, from the CFT that has nothing to do with gravitational physics. But the question is, can we somehow do better? Can we directly describe what's going on, for example, in the center, not having to rely on this sort of scattering experiments? The reason that this is important is, well, there are two empirical reasons that I'll describe that why we cannot be totally satisfied with the kind of scattering experiments that we do in this calculation. The first empirical evidence has to do with cosmology. There is, by now, quite compelling evidence that our universe underwent a period of very rapid exponential expansion in the distant past, and this was known as cosmic inflation. Part of the evidence is shown by the matching between theory and experiment in this case. Moreover, just recently our universe has entered into a phase or another period of exponential expansion. This is driven by the cosmological constant. So, conformally mapping our universe to a Penrose diagram, this is what our situation is. In such a situation, there is no scattering experiment for us to do, because everything we will see is confined within a finite volume. The reason we cannot go beyond that is because everything outside that volume is behind a cosmological horizon. So in such a setting, we can't do any experiment that is of the scattering type that we discussed earlier. We have to make sense of what's happening at the center, right here, right now. The second empirical evidence that we cannot be totally satisfied with just understanding scattering experiments has to do with the existence of black holes. The reason is that if some observer, so this is a Penrose diagram for the black hole, and here is a trajectory of some observer that falls into the black hole. An infalling observer has only a finite amount of space and time to make any measurements before they hit the singularity. So there's also no scattering experiment for them to do. So how do we describe what they see? There must be such a description. And I want to say that this is not a conceptual problem only. This is also a practical problem, at least for Alice and Bob, who live in perhaps very distant galaxies. And the only way for them to meet in their lifetime is for them to both jump into a nearby black hole that are connected by a wormhole. And of course, they would like to understand their behavior after they jump into the black hole, whether they are going to meet or not. And this is of practical use for them. And we'd like to have a description of their experience even after they cross the horizon. And for such situations, it is definitely not possible to describe it as a scattering experiment. I'd like to emphasize that, at least to me and to many of you, I think, that it is probably very likely that understanding this will teach us important lessons for cosmology. This is both because this infalling observer setting experiences a space-time which is fairly similar to a cosmological background, and also that, recently there is an argument that maybe consistency of quantum gravity requires the horizon of black holes to be singular. And this is sometimes called a firewall. If such a thing exists and the argument holds, it is really a blow to the kind of effective field theory argument or calculations we use in cosmology. We have the cosmological horizon, and we don't think anything special happens when observers cross those horizons. And you may be crossing a very distant observer's horizon. So if we don't understand this kind of problem, we have to really go back and rethink the things that we thought we understood before. Another reason that this is a good toy model is because in such a setting, actually there is a description of the theory that is more complete in the following sense. If I put everything into anti-de Sitter space, then there is a CFT description. And more generally, observers staying outside the black hole will have a complete description of the theory in terms of scattering amplitudes. So it's very tempting to think that there is some change of variables that helps us to go inside the black hole. And at least there is a set of variables which we can use to define the theory more completely. And it's therefore easier to solve this kind of problem than the full cosmological problem. So this is a step towards solving that problem eventually. So in the remainder, having motivated why we would like to understand the questions that we're going to ask, I'm going to focus on the following concrete question. How is the physics in the middle of space encoded in the fundamental degrees of freedom of quantum gravity? Now, I'd like to answer this question in the concrete setting of ADS-CFT correspondence, because this is the best understood model, and this is the best chance we have for understanding this question. Since ADS-CFT is a duality, we might think that there should be a way of map operators in the bulk to operators in the CFT. We should possibly be able to write down local bulk operators as CFT operators. But if we think about it, we run into a paradox. The paradox goes as follows. We know that in the quantum field theory, we have causality. And causality is enforced by locality, which is a statement that when two operators are space-like separated, they commute. Do a measurement here will not immediately influence a measurement at another location. We might expect this to be true also in the bulk. So we might expect that this is anti-de Sitter space, and we take a constant time slice, look at the bulk operator at the center, call that phi, and phi should commute with O, which because they're space-like separated, and this should work for any operator X, any operator O on the boundary. So it should be true whenever the 2 points are space-like. But it turns out this is actually impossible in the boundary CFT. This is because any quantum field theory satisfies the so-called time slice axiom. The time slice axiom says the following. It says any operator that commutes with all local operators on a fixed time slice would have to be a trivial operator. That means it's a C number. In different words, this means that the set of local operators on a fixed time slice acts irreducibly on the Hilbert space. So one way to think about this is to maybe think about the discretized version where I have a spin chain, and if I have products of Pauli matrices, they generate all the operators that can act in that system. What this means is that our bulk operator, now since it commutes with all boundary operators, or local boundary operators at this time slice, it should be a trivial operator, but that's not possible. We must be able to measure spin there is either up or down, but it cannot be the identity. So how can an extra dimension emerge if somehow we have this paradox? To make the problem even sharper, I'll do something you think that might be impossible. There is actually a formula for representing this bulk operator in the CFT. The formula is quite simple. So we have this anti-de Sitter space in the interior of the cylinder. Let's look at a bulk operator sitting at some location x, call that phi of x. There is a formula for representing phi of x in terms of a linear combination of local operators in the CFT. So these are O of y. And k is a smearing function that is being integrated over, and it's obtained by solving the equation of motion in anti-de Sitter space with certain boundary conditions. The exact details of what k is not terribly important. The important thing is that there is a k which gives a representation of the bulk operator as such an integral. And also the support of the integral is in this region, which is shaded. They consist of all the boundary points that is space-like, separated with respect to the bulk point. This is called global reconstruction because it uses all the information of the CFT. It uses every location. And also this is valid in the so-called large n limit, where n is the rank of the gauge group on the boundary. We can improve on this by including 1/n corrections. So there are terms that follow this leading term. These 1/n corrections can be incorporated order by order by essentially calculating Witten diagrams in this setting. Sorry, it's Feynman diagrams. Now, before resolving, so you might think that now I have a formula, I can just go ahead and compute the commutator and resolve the issue. Before doing that, let me introduce a second paradox, which is somewhat sharper, and that will actually lead to a resolution of both paradoxes. For the second paradox, I need one more tool, which is a more subtle version of the reconstruction that we have done on the previous slide. This is done on what is known as subregions. So the picture looks like this. We have the same cylinder. We have almost the same equation as before. So we also have about 0.5x. And in this case, we have a function which we only need to integrate over in a smaller region. So the way one should think about this is to take a t equals 0 slice of the boundary and separate the spatial region into some A and its complement. Then the domain of dependence of A, which is essentially the set of all points that cannot be influenced by A complement, is the region that I'm integrating over right now. This prescription works whenever the bulk point is reasonably close to this domain of dependence. Reasonably close means that it's in this wedge bounded by these two dotted surfaces. And these two dotted surfaces are null and meet at a geodesic connecting the two endpoints of A. In higher dimensions, it would be a minimal surface as opposed to a geodesic. So this is a wedge that is called the Ringler wedge of the region A. This construction is therefore also called Ringler reconstruction. And the two reconstructions that we have mentioned so far, the Ringler reconstruction and the global reconstruction, are related by a Bogoliubov transformation in the bulk. So they describe the bulk operator. They describe the same bulk operator. But the Ringler reconstruction is more powerful in the CFT. This is because we might, for example, use this kind of relation for computing correlation functions of phi. And then we translate that correlation function into a calculation of correlation function of local operators in the CFT. If we do it in the Ringler reconstruction, then all we need to know is the CFT state on the region A. We don't need to know the global wave function everywhere. We just need to know the reduced density matrix of the CFT on the subregion. So only a limited set of data is needed for using this kind of Ringler reconstruction. This is quite important. So let me also demonstrate what's happening if we look at this from above. So let's focus on a constant time slice. And region A is here. A complement is the rest of the system. We have a geodesic connecting the two endpoints. And for all operators in this shaded region, which is essentially the Ringler wedge constrained to this spatial slice, all the operators in the shaded region can be reconstructed on A. All operators in this unshaded region cannot be reconstructed on A, but it can be reconstructed on A complement. It's quite amazing that for a given operator like phi of x, I can choose A in many different ways. As long as A is big enough so that its Ringler wedge contains the bulk point, I will be able to do this. This immediately leads to the second paradox. The second paradox involves the following picture. So let's divide the boundary into three regions, A, B, and C. Now, each one of them will have a rather small Ringler wedge. For A, it will be this shaded region. So it doesn't contain the center. This means the operator in the center cannot be represented on A or on B or on C. However, if we take a union of any two of them, for example, let's consider A and B, the union of A and B, its Ringler wedge will be rather big. It will contain this big region, and in particular, it will contain the center. So according to the rules that we set so far, phi at the center can be represented on the union of A with B. And by symmetry, it can also be represented on the union of A with C and union of B with C. But the three representations that we have for the same operator in the center, let's call them phi AB, phi BC, and phi AC, they cannot be the same operator in the CFT. They don't even have any common support. So somehow what we have done is to take the same operator in the bulk and mapped it to 3 different operators in a CFT. So how can this happen? Where is the information describing the center located in the CFT? Let me summarize what we have so far. We have 2 sharp paradoxes. One is about the commutator between the bulk operator and local operators on the boundary, because they seem to commute on the fixed time slice, but this is impossible because of the time slice axiom. The second is that the same operator in the bulk can be represented by 3 different operators in the CFT. It was understood in the past 2 years that these puzzles can be solved by interpreting ADS CFT as a quantum error correcting code. So let me first introduce what's a quantum error correcting code. These codes were invented to prevent quantum computers from decoherence. In particular, the idea is that we should protect the quantum message by encoding it in a non-local pattern of entanglement between many degrees of freedom. There is actually a very beautiful theory of quantum error correction that I can tell you today, but let me instead focus on a very simple example. And it turns out that simple example is also a very good toy model for holography. The toy model is the so-called qubit model. So the idea is that I want to send you a state that describes a single qubit. A qubit is a 3-dimensional version of a qubit. So a qubit takes either 0 or 1 or their superpositions. A qubit has a 3-dimensional Hilbert space. So this is a general state of a single qubit with basis labeled by K. I want to send you that state by mail. And as we know, mail is never reliable, so it may get lost or corrupted. If this is a classical message, I can just copy it many, many times, send you all those copies, and if you at least receive one of them, you get message. But quantum mechanically, I cannot do that because of the non-cloning theorem. The proposal is instead to encode the message in a larger system. In this case, I need 3 qubits to make it work. The 3 qubits has a 27-dimensional Hilbert space. I'm going to send you a single qubit state, so that means I'm going to embed the state in a special 3-dimensional subspace, and that's the code subspace. So the code subspace is going to be the set of states for which there is a valid message. There is a valid underlying message to be decoded. I'm simply going to define some basis for this code subspace and call it K tilde and encode the state using the same coefficient. So that's the state I'm actually going to send. To be very concrete, I can tell you the basis elements, 0 tilde, 1 tilde, and 2 tilde. In terms of states of the 3 qubits, this is a particular choice. It's a very nice choice because under this choice, the subspace is completely symmetric between the 3 qubits. And each state is also very entangled. It is so entangled that if we take any state of the subspace and look at the density matrix on one of the 3 qubits, we get a maximally mixed state. In other words, there is 0 information in any one qubit about the encoded state. By looking at just one qubit, I can get 0 information. This leads to the surprising feature that it's actually possible to recover the full information from any 2 qubits. So let me demonstrate that. I'll define this unitary operator that acts on 2 qubits in this way by acting on the basis in the following way. And I'll call it U12 just to denote the fact that it acts on the first 2 qubits. So it's a homework problem to check that if I act U12 on the state K tilde, I'll simply decode the state and put K into the first qubit. and get some universal state chi in the remaining qubits. Chi is written in this way. It's not terribly important. The important thing is chi is independent of k. So therefore, we can recover any state, because we can just do this under superposition. We can recover any state in the code subspace by using the same decoding operator. By symmetry, we also have U23 and U13. So we can recover the information from any two of the three qubits. This is already very reminiscent of our ABC example before, where we have the operator in the center and seemingly have three different realizations of that on the boundary. But there we talked about operators instead of states. But we can easily remedy that. So let's say we want to talk about operators. We want to implement a single qubit operator O that acts on the code on the qubit I'm trying to send. This is an arbitrary operator denoted by some matrix elements. We want to implement this operator as a 3-qubit operator, O tilde, but acting on the code subspace. So by definition, this is a correct implementation if we succeed. There are many ways to implement the same operator O on the Hilbert space. O tilde is not unique. And if we make a random choice, we will generally have an O tilde that acts on all three qubits. But we can do better. In particular, we can use this U12 and choose a special realization of O tilde. Let me call that O12. So what it does is essentially to first decode the state using U12. So that put the required state, the underlying state, into the first qubit. And then I'll act O, the desired operation, on that qubit. This is O1. And finally, I'll re-encode the message. So this is a way to act on the state in this encoded way on the code subspace. Again, by construction, O tilde 1, 2 acts on only the first two qubits, but it still implements O on the code subspace. Now, by symmetry, I can define similarly O23 and O13. So the statement is that they are different operators. They act differently if we consider all states in the Hilbert space. But on this special three-dimensional code subspace, which has a physical information about the underlying qubit, they act in the same way. This is what happens in ADS-CFT in the previous ABC example. So by using entanglement in the code subspace, we have precisely reproduced the kind of puzzling properties of subregion duality that we saw earlier. So this is the picture we had earlier. Now I'd like to write the qubit model in this way. In particular, the three physical qubits that I'm sending to you actually by mail are the local CFT degrees of freedom on the boundary. So they correspond to A, B, and C on the boundary. There is one logical qubit that I'm trying to encode. That's what's represented by the three-dimensional code subspace. So that's the operator in the center. We have different realizations of the same bulk operator on the boundary. So we had Rindler reconstructions tells us three different operators, phi AB, phi BC, and phi AC. They are really the different implementations of the same underlying logical operation under different parts of the system, the O12 that we saw earlier, O23, and O13. So we have seen explicitly how to produce the same kind of behaviors that we saw in the gauge gravity in the ADS-CFT case. So the interpretation of all of that is that in ADS-CFT correspondence, the various different ways of representing the same bulk operator are different CFT operators, but they act on some code subspace in the same way. This is what we really mean by this Rindler reconstruction. This is what we mean by subregion duality. So when we write down this equation of phi equals the integral of something, we should be thinking of it as in the quantum error correcting code way, rather than in terms of an operator equation in the CFT. So this solves the second paradox, the paradox that we seem to have different ways of representing the same operator and how they are related. I can also solve the first paradox about the commutator. The basic idea is that the commutator that we saw earlier does not generally vanish. It only vanishes inside this code subspace. So to see that, so first, if it doesn't generally vanish as an operator equation, then we can get around the time slice axiom. So that's good. We can also see why it vanishes in the code subspace. So in this Qtrit model, we can take an analogous commutator of O tilde, some operation on the underlying Qtrit, and x3, which is an arbitrary operator acting on, let's say, the third Qtrit on the boundary, this third physical Qtrit. And we can consider this commutator. If we just consider this commutator as an operator, it's not zero, but we can sandwich it using states in the code subspace. Once we do that, we can replace O tilde with a specific realization. For example, O12 tilde that we saw earlier. And once we do that, obviously O12 tilde will commute with x3 by definition. So we have seen that now we can consider x1 or x2, and we have seen that within the code subspace, O tilde actually commutes with all local operators in this setting. This is the feature that we have seen also from ADS-CFT, that above operator in the center seems to commute with all local operators in the CFT and a fixed time slice. And this is the explanation for that. So we have solved both puzzles by interpreting ADS-CFT as a quantum error correcting code. In particular, you can ask what's the code subspace in the ADS-CFT context. In this case, it consists of all states that are well described by low energy effective field theory in the bulk. Those are the states which we are normally interested in. That's the states, for example, the room is currently under. And that's the state which we are most used to describe because we understand how to describe them using GR plus matter field and other couplings. However, we shouldn't expect all CFT states to behave in such a way. So only a special subspace of states belong to this class where we can use a low energy effective description. In this sense, the Qtrit model is a toy model of holography where we have an emergent Qtrit that comes out of three physical Qtrits. And the Qtrit emerges only in this subspace. In fact, there is no sense of this Qtrit if we go out of the code subspace. So the fun doesn't stop here. We can ask, what about states outside the code subspace? What's the interpretation of those states? In the Qtrit model, there is a 24-dimensional subspace orthogonal to the code subspace because the total Hilbert space is 27-dimensional. What do these states describe? This is where gravity comes in. They are microstates of a black hole which has essentially swallowed the bulk point. So the bulk point is behind the horizon, and in fact so far behind the horizon that we can no longer account for it. This is similar to the Qtrit model, where if we go outside the code subspace, we simply don't have, it's an invalid message. If I'm sending that to you and you receive it, it doesn't mean anything to you. It doesn't contain an emergent Qtrit. And in the gravitational side, black hole states are those states where it does not make sense to talk about operators far behind the horizon. So this is a description of black hole states in terms of states outside the code subspace. So far we've seen a few things, and let's pause and remember that. First, we have seen how to interpret ADS-CFT or holography in general as a quantum error correcting code. In particular, we have used this reinterpretation to solve our two paradoxes by restricting to the code subspace. Once we restrict various statements to the code subspace, we no longer get a contradiction. Furthermore, we have gained some understanding about the quantum nature of black holes by rephrasing them as states outside this code subspace. So from all of this, we can actually derive many concrete results. I don't have time to go through all of that today, but let me mention a few highlights. The first is that the code actually has the property that quantum information located further from the boundary are better protected in the CFT. So in this picture, the operator furthest from the boundary is one in the center, and is best protected because you can erase many small systems, and you can still recover the information from the rest of the system. For example, you can erase this part of the CFT, or change the state, or do anything on it, but you can still reliably recover the operator here by using the complement of the region that you've erased. The situation is worse if we consider an operator closer to the boundary. For example, if we have that an operator, then erasing just a small part of the CFT, this part, would destroy any description of it. So operator at the center is better protected, and in fact, it requires roughly erasing half of the system in order to destroy the information. This actually provides a very precise realization of the correspondence between the radial direction in ADS with the energy scale in the CFT. The idea is that radial distance should be thought of as whether we are talking about high energy or low energy excitations in the CFT. Excitations very close to the boundary should be thought of as high energy excitations in the CFT, whereas deep in the bulk, things are low energies in the CFT. But this is a very precise realization of that. One can, instead of talking, you might think, what is the precise definition of low energy and high energy? That would actually gives a sharp definition of radial distance in this case. That's a very difficult question, actually. But this is a very precise realization of that, because asking whether a given operator is protected from certain kind of errors, whether it can be recovered from what you have left, this is a very concrete statement. It's either yes or no. So I can go further, and in fact, it's possible to see this by generalizing the Q-trip model. The Q-trip model is really a very coarse-grained version of ADS-CFT, where I've essentially coarse-grained all the boundary data, the entire boundary CFT, into 3 points, and 3 Q-trips even. And all the bulk degrees of freedom is coarse-grained to 1 bulk point. There are more intricate models built from tensor networks recently and resemble ADS-CFT more closely. So you simply do this in a more organized fashion, and where you can see that operators, for example, at the center, is more protected from operators sitting closer to the boundary. We can also ask how large the code subspace can be. In particular, we can ask how many states can we realize the algebra of the bulk operators. It cannot be the entire Hilbert space, because they would involve states that has black holes for which the bulk operator does not make sense. It turns out this question is answered by a general theorem in quantum error correction. I won't bore you with all the details, but I'll tell you that the answer actually matches with the bulk regime where we make a black hole. So it's precisely you fail to realize if you try to make more and more states, include more and more states in the code subspace, at some point you cannot realize the algebra of bulk operators, and that's precisely when we make a black hole. Therefore, I think the code reinterpretation has provided something very precise. It makes precise a point that we had in the beginning, that even though low-energy observers like us sees fairly local physics, if we try to make sense of space-time too precisely, if we try to make a measurement very, very precisely, it will create a black hole, and we lose control. But we have known this for many years. I think it's really amazing that using the quantum error correcting code picture, you can make this precise. You can see in what sense the realization of the operator has failed to satisfy the required locality property, because you have gone from a code subspace into states which are outside the code subspace, which describe states that are not satisfy low-energy effective field theory. So this is the thing. One of the things that I really think that changes our perspective on understanding quantum gravity, and it's also very nice to see that in this context we need black holes for the story to be consistent. If we don't have black holes, then our paradoxes would be true contradictions, and therefore, we will not have a consistent theory. So, in fact, it's only for quantum gravity that a higher dimensional theory can be equivalent to a lower dimensional one. So this answers my second question that I introduced at the beginning. I also want to mention that reinterpreting holography as a quantum error correcting code has led to a lot more understanding about how to reconstruct bulk physics. In particular, it has made it possible to reconstruct bulk physics in situations more general than the Ringler case. We discussed how to do that in the Ringler case, but we can actually do that much more generally. The useful thing that comes out of this is that it allows us to reach deeper in the bulk than we normally can. And in particular, it can even sometimes allows us to reach behind black hole horizons. So this comes back to one of our questions before. Can we somehow describe the experience of some infalling observer? To some extent, quantum error correction allows us to do that. So I won't go into all those details, but I want to mention that this was impossible using our previous understanding of holography. So I think this signifies a conceptual change. This is actually related to many aspects of a very fascinating connection between quantum entanglement and space-time geometry. And this includes, for example, the so-called Ruktak-Yanagi formula. It simply says that in the context of holography, if we look at the entanglement entropy of a subregion, it is described by the area of a minimal surface in the bulk, in the dual space-time. And also it's related to the so-called ER equals EPR conjecture, which translates into the statement that wormhole is equal to entanglement. There are many interesting questions about how the code works and how they describe gravity in detail. I think many of them still remain to be explored. And a key question I'd like to emphasize is how far behind the black hole horizon can we actually go and maintain local physics, maintain approximate locality? This is, so I've mentioned that there is a certain sense that we can already go behind black hole horizon using the current quantum error correcting picture, but we'd like to push on that as far as possible. We'd like to understand what happens maybe deep behind black hole horizons. Finally, let me also come back to cosmology, because I think this is the really important thing that we should keep in mind. So this is our universe, and we're over here, and we have a cosmological horizon. Today, we did some analysis in ADS, which is not our universe. But the analysis was possible because we understand ADS CFT to a great amount of accuracy. We understand it from string theory. It's well formulated. We can pose very sharp questions and answer them in a very sharp way. We don't have that yet for cosmology. We don't have a framework for understanding quantum gravity completely in accelerating universes like the pseudospace. So I think one promising direction is to find simple compactifications from string theory that will lead to solutions with accelerated expansion, something similar to our universe. And this would provide a stage for studying what we did today, but in the context of cosmology. For fun, I'll close with the observation that ADS-CFT provides a kind of quantum error correcting codes that are rather new and special. And first, there's a great amount of organization in how the degrees of freedom are organized, as you may have noticed from the tensor network models. But also, necessarily, by the very virtue of how ADS-CFT works, it comes with a large number of degrees of freedom. So in the language of quantum computers, it's a very large number of qubits. And we know that this is something that's one of the technical difficulties in getting quantum computers to work. So perhaps they're useful for something. Perhaps this way of thinking about quantum gravity will lead to exciting applications in unexpected areas, such as quantum computation and deep learning. Thank you.
Thank you very much. Are there any questions? Maybe I'll start with one. So at one point you were describing states that are outside the code subspace.
Yes.
And said that they were black holes.
Yes.
But presumably there are sort of excited string states and things involved that would also be outside the code subspace. They're not low energy excitations.
So in general, yes. In general, any state that is not well described by a low energy effective field theory in this way of thinking about things would be states outside the code subspace. So as long as a state does not admit such a nice description, for example, it could be highly excited string states, I would say they're also outside the code subspace. Now, most of the states outside the code subspace should probably be thought of as black hole states. This is what I mean.
Okay. Any other questions?
You had mentioned the black hole firewall, which is the idea that you fall into a black hole as soon as you cross the horizon, you
Yes.
hit something. And then at the end you were saying you think you can look inside the black hole. So
those are special black holes. So
Sorry?
those are special black holes.
Okay.
Yes, in the context where I said at the end, where I say one can reconstruct operators even behind black hole horizon, those are special black holes created by a path integral, created by a collapse, which we know that at least for a short amount of time there is no firewall. So I think that's why I was trying to go beyond that and ask how far behind the horizon can we push this? Because that will eventually go into the regime of the firewall and can resolve the firewall paradox.
do you have an opinion on the firewall paradox for a Schwarzschild black hole in our space?
I have some opinions.
You have to ask if he would jump into a black hole.
It depends on what the black hole, when the black hole was created. Well, okay. I have some opinion which we can discuss in detail.
All right.
Yes.
Are there any implications for classical error correction? Because certain dimensions have very dense sphere packings, which
Yes.
are mapped to classical error correction.
Yes.
8 dimensions, 24 dimensions.
Yeah, I know that fact. I haven't really thought about how this connects to classical error correction. at all. So, no, I don't know. Honest answer, I don't know. I hope this is something that I think would be interesting to explore, but I don't know. That's a good question.
So it seems that the codes are correcting codes that you're talking about were like erasure codes, right? Where
Yes.
You've got a bunch of them, a bunch of qubits are taken out.
Yes. Yes.
Is that? But you also have other kinds of codes that deal with other kind of errors. Do they play
Yes.
a role too in this story?
Right now, most of the codes that we encounter in this discussion are indeed erasure codes. So I haven't seen a very concrete case where other more general types of codes comes into this, but I wouldn't rule out that possibility. The reason is that in ADS CFT, there is a locality property in the CFT. So it makes a lot of sense to talk about local erasures. Whereas in a perhaps more non-local setting, perhaps matrix theory, it would make sense to talk about other kinds of errors.
Well, if there are no further questions, let's thank the speaker again.